to have, it's really a pleasure to have Matt Schrecker from University College London, and he will speak about gravitational collapse for Newtonian stars. So please, Matt.
Thank you. Thanks very much for the invitation. It's a pleasure to be attending this conference. So as you can see, my title is Gravitational Collapse for Newtonian Stars. And so I want to start by talking about what this model I'm describing is. So we're really starting from the classical model of a star. So I have some sphere of gas with Newtonian gravity, and there's initially a balance between the pressure and the gravity. So pressure is pushing stuff out, gravity is pushing stuff in, and for some time it's going to be roughly in balance, and so we'll have a static star. But as the gas burns, this balance shifts, and then there's a number of things that can happen. One of those is that gravity takes over and everything crunches down, and we have this possible collapse scenario, and this is the scenario I'm particularly interested in here. So I've got a sort of schematic diagram here of what's going on. So this is starting with this classical onion layer model of a star. So we have lighter gases towards the outside, denser gases and metals towards the inside in a sort of layered structure. And then as the collapse procedure initiates, the gas starts moving inwards radially. So I will assume radial symmetry throughout. And what happens is the gas moves at different rates in different parts of the star. So these black arrows here, these are describing a supersonic collapse, so gas moving faster than the local speed of sound, while the white arrows here describe a subsonic rate of collapse, which makes sense if you think that the speed of sound depends on the density, and the density is highest at the center of the star. At a certain point, we reach some critical time where the star is at its most collapsed. And one possible outcome then is the formation of a shockwave and a supernova. And that's what this second row of the diagram is describing. A shock forms, that's the red circle here, and it ejects. If there was enough initial mass, it ejects through the whole of the star and is released as an expanding spherical shockwave. So for the purposes of this talk, what we're really interested in is this first row of the diagram, really the collapse scenario, and how we can describe this mathematically. So to do this, I said I'm talking about Newtonian stars, and so I'm going to use the Euler-Poisson equations. This is gas dynamics plus Newtonian gravity. So just to fix some notation here, I've got the conservation of mass, rho is the density of my star, u is a vectorial velocity here, though I will assume symmetry later on. So this first equation is just the standard conservation law for the density. The second equation, if we kill off this right-hand side, this would just be the standard barotropic conservation of momentum equation. So I have some rho u is momentum, there's a convective term, and nonlinearities appear here in the convection and also in the pressure, which I'll just be assuming to be some polytropic equation of state. With the right-hand side, we have the action of gravitational forces as well, and these are driven by a potential. So Euler-Poisson equations, the potential solves a Poisson equation. Laplacian of phi is governed by the density. So gravity acts acts on the momentum weighted with density, and it's solving a Poisson equation forced by the density. So this is the standard model that we're dealing with. It's a very classical model. And the equation of state I'm talking about to close this system for the pressure is this P of rho is rho to the gamma. So of course I could put a positive constant here. I'm just going to treat it to be 1 for the purposes of this talk. It's not hugely important. What is important is the range of exponents. So I'll come on in a moment to why we need this particular range, but these exponents come up for all sorts of different physical reasons, as I'm sure many of you already know very well. 5/3 is the classical exponent predicted by the kinetic theory of gases for a monatomic gas. In astrophysics, it's also used for fully convective star cores, red giants, these sorts of things. 4/3 is another sort of key number that will crop up again and again through this talk. And it gets used for high mass white dwarf stars. It gets used for main sequence stars. But in general, the principle to bear in mind, I said that the density is distributed such that I have a whole sequence of different gases with increasing density towards the center of the star. I'm smoothing out the overall pressure law for these. And what happens if I take this polytrope approximation is that as gamma decreases, I'm expecting the density to be increasingly weighted towards the center of the star. So for very massive stars where I have very heavy metals in the core and a lot of mass, I expect that weighting to force in and gamma to decrease. So that's the basic modeling assumption. What I mean by collapse, to be a bit more precise, is the formulation of a singularity at the origin. So we're really going to go all the way to blow up of the density. So 0 is my spatial origin. I'm sending time to 0 from below. So 0 is the blow up time. And it's been known since a work of Taiping Liu and collaborators in 2002 that for gamma bigger than 4/3, they're able to rule out collapses with finite mass and energy. And so we're not really looking for collapse in that regime. More interesting from this point of view is the critical case, gamma equals 4/3, where since 1980, these so-called Goldreich-Weber solutions have been very widely studied. So this is a really interesting family of solutions of the Euler-Poisson equations. They come from an ODE analysis. There's a partial separation in the equations if you work out what's going on with this particular exponent. But these have been criticized by astrophysicists as unsuitable models for the outer core, so this supersonic collapsing region. So these are a sort of broad family of possible solutions with different behaviors. What we're going to look at is what happens if we push gamma below this to the threshold that astrophysicists have really investigated since the late 60s. So I have a little GIF that's really the second half, the supernova expansion, but it shows some of the key features that I want to talk about. So here you see the star immediately pre-supernova expansion, and then you see this roughly spherical shockwave expanding. So I will stop that for a moment. You can imagine that if you fixed your camera at the origin, and if you zoomed out at a particular rate, what you would see is not an expanding shock, but a static shock. And this is partly to do with the spherically symmetric assumption, but it's also telling you something about the underlying scaling symmetries of the problem that we're really going to use. So if you imagine a time-reversed version of this without the shock wave, for the collapse procedure, you can imagine rescaling the problem as the star collapses to blow up so that you have a roughly static picture. And this is connected to the so-called self-similarity hypothesis that's been conjectured by astrophysicists, where they say that as the star collapses, you really expect the limiting profile as it collapses down and as the density blows up to be a roughly self-similar solution of the Euler-Poisson equations. So these self-similarities, this is of course one of the themes of the conference, so I don't really need to tell you all of this, but the self-similarity and singularity formation interact in a very wide range of problems. Obviously, I'm talking about stellar collapse. In gas dynamics, the formation and expansion of shock waves also has or can have a self-similar flavor. There are self-similar solutions to the Berger's equation that can be taken as leading order shock formation profiles. The shock reflection problem, which has been studied fairly extensively recently, is another problem where singularities actually propagate in a self-similar manner rather than just being formed in a self-similar manner. But this also occurs in droplet pinch-off. So what I'm talking about here is I take a long thread of a viscous fluid, and if the sort of radius of the thread is sufficiently small, these are subject to the famous Rayleigh-Taylor instabilities, where if I start introducing small perturbations, these perturbations will amplify and eventually pinch off the thread to form into a series of little satellite droplets. And again, here we can find actually universal exponents governing a self-similar blow-up of something and topological change in the structure of the solution. These are studied also in models of bacterial growth, reaction diffusion equations in particular, geometric wave equations, the Yang-Mills equation very recently. There have been stability analyses for self-similar blow-up solutions. It's a whole series of these problems. And the key features across all of these are, of course, the nonlinearity of the problems, the intertwining of the spatial and time scales, by which I mean sort of the rate at which time and space need to be rescaled to see these self-similar solutions. And of course, the fact that good initial data, which for us will be smooth and bounded, leads to blow-up solutions. So not just the formation of shock waves, which would be singularities in the derivative, but really a blow-up in the fluid variables. So this is all sort of motivation. Let me get a little bit more precise. I'm supposing radial symmetry throughout this talk. So the density is going to depend on time and some radial coordinate, r is distance to the origin. Velocity is some scalar times the radial unit vector. So rho and u are now my variables. Let's suppose we have some solution of Euler-Poisson and a scale lambda, which you should think of as kind of like the rate of concentration. So the amount we have to zoom or blow up to see what's going on at the dominant scale. So if I make this scaling, rho lambda is lambda to the minus 2 on 2 minus gamma. And remember, gamma is between 1 and 4/3. So this exponent here is positive with the minus sign negative. So this is, as I send lambda to 0, this is going to blow up. T over this factor of lambda and r over lambda. And similarly for u lambda, then we get another solution of Euler-Poisson, though of course with possibly different data. It's important to note that this is a unique scaling for the Euler-Poisson equations. If I kill off the gravity, there is in fact a 2-parameter family of scalings for the pure Euler equations. And this is an important fact that's been exploited for a number of different problems. Here, the gravity and the pressure, which is of course the thing telling me what gamma is, they interact in such a way as to fix this scaling. The hope now is I want somehow to be sending lambda to 0 such that on smaller and smaller scales, I see larger and larger densities. So think lambda's tending to 0, this is going to blow up. The hope is if the density is positive at the spatial origin, then if I send lambda to 0, the density will actually tend to infinity. So to get out a self-similar profile, we make the obvious ansatz. We find the combination of time and space that respects this scaling, which is, of course, this ratio. I have a negative t here because I'm sending t to 0 from below. And I search for my solution in this self-similar form. So I have some prefactor, which will tend to infinity as I send t to 0, but then a profile depending only on the self-similar variable y. So this is the ansatz we're going to make to try and hunt for solutions. Before I show you what the ODEs are, I should talk about what happens when we make these scalings to the significant physical quantities. The first of these is the mass. This is obviously just the integral of density over R3, or in radial coordinates against R squared dr. And the energy, where I apologize, I've lost this factor of a half from the kinetic energy, potential energy, and then a term arising from the gravitational potential. The mass, of course, is non-negative, and it scales according to this exponent. And you see now here, gamma is 4/3, is exactly the mass critical scaling for this problem. While for the energy, 6/5, this is a simple computation, is the critical exponent. And so the range between 6/5 and 4/3 is particularly interesting for what we want to do. because the basic self-similar profiles without any additional cutting off or dampening are going to have this nice finite energy condition. Other important thing to note here is that the energy is not necessarily positive definite. Phi solves a Poisson equation forced by rho, so I can replace this rho with a phi here, or Laplacian phi, sorry, integrate by parts, assuming some reasonable asymptotic behavior. And what you see is a negative definite contribution to the energy. And this is a part of the reason that we can expect blow up to happen if this gravity starts to dominate. Okay, so if I make this ansatz, the self-similar ansatz, then I can, after some manipulation, rewrite the basic equations in this ODE form. So all the scaling factors drop out. So here I'm defining for convenience a variable omega in terms of the velocity. This isn't a completely arbitrary choice of function. It firstly gives us this nice form for the equations, but also y omega, so u tilde plus 2 minus gamma, is a sort of pseudo velocity. It's referred to in the astrophysics literature as the wind speed, and it plays an essential role on in the equations down here, as I'll explain in just a moment. The nonlinearities appear in a number of places. We have this one nice linear but singular term of a kind that looks like it will be amenable to a Frobenius analysis. And then we have nonlinearities h and this denominator. H I haven't written down, it's a slightly ugly form. It's a quadratic in rho and omega, so quadratic in both.
So I have a question. Can you please go back to what you call self-similar Euler-Poisson?
So this is the self-similarity.
But you didn't write the equation, right? Okay, because I was looking whether there was an equation. Okay.
So if
right.
you...
So, no, you just write the Euler-Poisson, right?
Yeah. So Euler-Poisson was this.
Yeah, one. Yeah.
If you substitute in here the self-similar ansatz, which is this ansatz, you're looking now for ODEs just in Y, and that's exactly this system. This is self-similar Euler-Poisson.
Okay.
So when I say self-similar Euler-Poisson becomes, what I mean is the Euler-Poisson equation under the assumption of self-similarity is this ODE.
Right. Is this, right? Exactly. Yes. Okay.
So
could you explain the appearance of that term in the denominator? Like, do you have an explanation about why it comes?
I do. So now yes, that's what's going on with this definition.
Yeah, but how it comes? Like, how you explain that it comes?
So what this is doing is in the self-similar coordinates, what this is telling you is really about the type of PDE you have. This is a hyperbolic elliptic transition. So this singularity, so what if I give you the physical meaning of this gamma rho to the gamma minus 1 is the square of the speed of sound. The y squared omega squared, this is the square of the speed of the wind speed. So what this is saying is when wind speed is bigger than the square of the speed of sound, you have a supersonic flow, so a hyperbolic problem. When it's less, you have a subsonic flow, and so an elliptic problem in self-similar coordinates. So that's what the coordinate, that's why this appears in these self-similar coordinates. It's because you introduce a type change into the underlying system. So I'll talk about this a bit more later, but if you linearize around the profile I'm going to produce, you can really see a degeneracy that crops up with exactly this kind of weight. And the sign of this is telling you the type of problem you have. Does that answer your question a bit?
Yeah, I think that's fine.
Okay, so because we have this singularity, and for the reasons I just explained, we call sonic points where this denominator vanishes. So a point where it vanishes, as I've said, is one where the wind speed is equal to the local speed of sound. And from the schematic diagram I showed you initially, we expect at least one of these to occur. I expect supersonic flow in an outer core and subsonic flow in some inner core. And so we expect to have to deal with at least one transition of this kind. And the hope is that we will only have to deal with one. So that's a very hand-wavy physical explanation for why we expect this to be important. On a mathematical level, it's essential because if we don't know the location of such a sonic point, it's a possible singularity in the ODE problem that we want to avoid. But it also turns out from natural boundary conditions that I'll show you in just a second that such a condition is inevitable. So I'm looking for regular solutions to this ODE problem, in particular regular at the origin and with the density decaying in the far field, so tending to zero as I go out to infinity. And in the first instance, for omega to be regular at the origin, I need the value of omega to be constrained to be 4/3 minus gamma. Otherwise, this term will be singular. So that's going to be my first boundary condition. And the density I want to be positive, strictly positive. Otherwise, I'm not necessarily getting my singularity as I allow the collapse to proceed. So these are the first boundary conditions. These are, in some sense, initial conditions for the ODE system, which are going to be the things that give me a regular blowing up solution. In the far field, I want the density to decay. And in fact, the rate of decay is going to be algebraically constrained by the structure of the nonlinearity in the equation. This is really an exercise if you look at the precise structure of the nonlinearity that I haven't written down. And likewise, the limit of omega is going to have to be a positive constant. And this constant is bigger than this one. This is 2 minus gamma. This is 4/3 minus gamma. So this forces the existence of a sonic point. Because at the origin, I have density positive, y squared omega squared is going to be 0. So the sonic condition will be positive. I'll have a subsonic flow. In the far field, the omega tends to a positive constant. So y squared omega squared tends to infinity. Density tends to 0. And so if I just return to this condition, this y squared omega minus y squared omega squared tends to negative infinity. Rho to the gamma minus 1 is positive. And so the intermediate value theorem tells me any continuous solution will have to have at least one sonic point. And this is exactly this transition. So what's the theorem? Well, the theorem is that for any gamma that you give me in this range 1 to 4/3, there is a solution which is global in y, so all the way 0 to infinity, of the self-similar Euler-Poisson, which has one and only one sonic point. The density is positive everywhere and satisfies this asymptotic behavior. The radial velocity is negative everywhere, so the gas is moving in everywhere. It vanishes at the origin. And in fact, I have monotonicity for both density and this omega, the pseudo-velocity. The density monotonicity is telling me that I have the most density at the origin and then the profile decays as I go out, which is what I expect physically. The monotonicity of omega, I'll talk about more later. It's important both for possible stability considerations and for, in fact, the proof of existence of the solution in the first place. So this is the basic result, is to get this smooth solution, real analytic solution.
So, can I ask another question? Like concerning the condition at infinity, what's the physics behind them? Like,
if you look at, just suppose you have some solution that lives all the way out to infinity and is supersonic, you find that you are forced into this as an attractor, basically. So it's also saying you want the density to decay rather than to grow. so that you have some hope of finite energy, or a possibility of a truncation to get finite mass. I mean, solutions where the density tends to infinity at infinity are obviously non-physical.
Yeah, but here at the end, the solution you are getting is not finite mass.
It's not. You could dampen it without doing too much damage to the actual solution. But no, it will be finite energy if gamma is bigger than 6/5. The tail does not decay quickly enough to have finite mass. So this is discussed in the astrophysics literature, which I'll refer to in a moment.
Right. Okay.
Yeah. But I mean, the basic point is that you hope that if you're far enough out, you can dampen the tail in such a way that you don't interfere with what's going on in the center.
And the value of omega of 0, again, the 4 minus 3 gamma over 3.
That comes from the smoothness requirement. This term is going to vanish. The numerator has to be 0. Otherwise, you've got a singularity.
Yeah. Okay.
So this is constrained by regularity. Okay, so here is the astrophysics literature. The study of sort of imploding solutions for the pure Euler equations goes back a long way. There's a whole series of works in the 40s that are particularly influential, independently by Taylor, von Neumann, Sedov, and Gödeli. These are considering shock solutions, so with shock waves, but they exploit the two-parameter freedom for the self-similar scaling in the pure Euler equations. So the Gödeli solutions in particular consider a spherical shock wave that's focusing on the origin, and as it does, the strength of the shock increases and various quantities blow up in finite time. Of course, here we're looking for smooth solutions, so no shock waves. And so the first work for Euler-Poisson of this kind is by Laston and Penston independently, I should say, in 1969, where they take the isothermal gas dynamics, so gamma equals 1, and they solve for a numerical solution of the self-similar Euler-Poisson, so trying to get a blow-up solution in this isothermal case. There is then a whole series of other works, a particularly important one of which is Hunter from 1977, who produced a family or numerical evidence for a countable sequence of solutions. So then there was this question, which are the stable solutions, which are the unstable solutions? This went on for some time with various numerical investigations, and this work of Maeda Harada in 2001 finally produced numerical evidence for mode stability of the original LP, Larson-Penston solution, and of instability for the Hunter solutions in the class of radially symmetric functions. So these are all in radial symmetry. All of these isothermal solutions, however, were criticized by Yahil, and this is going back to the finite mass and energy consideration. Yahil said that because the energy of these solutions, as well as the mass, is infinite, he criticized them on physical grounds, as well as the fact that you expect for the kinds of stars or the kinds of density profiles that you hope to see, you want a wider range of gamma, not the purely isothermal dynamics. So to allow some greater flexibility in the modeling as well. So in 1983, Yahil constructed numerical blow-up solutions, these self-similar imploding solutions, for exactly this range of gamma, which is contained in the range that we're studying. Much more recently, this work of Mel, Raphael, Rodniansky, and Sheftel, this is a series of works. They proved the existence of implosion solutions for the pure Euler equations without gravity, again using a self-similarity ansatz. They, in fact, show the finite codimension stability of these works in radial symmetry. And Guo, Hadzik, and Zhang, who are, of course, the people that I did this work with, they constructed the original LP, the Larson-Penston solution, in the gamma equals 1 case. So these are recent analytic works. The key difficulties here, firstly, we want a smooth solution rather than a solution of finite regularity. And we expect that the stability of the solutions is tied very closely to the regularity. There's in fact a paper from the 80s by Whitworth and Summers on CK solutions to Euler-Poisson, where they allow for sort of kinks in the solution, and these are expected to be highly unstable. So I think not even finite codimension stable, but really unstable. The smoothness, because I'm looking at an ODE problem, is of course not so much a problem for most of the domain. There's a slight issue at the origin, but that's going to be fine by Frobenius methods. It's really through the sonic point that we have questions about smoothness. The nonlinearity means that we need methods adapted to specific nonlinearities. This is, of course, the case with all nonlinear PDE problems for the most part. But I really want to emphasize here that because the sonic point is a movable singularity in the equation, that is, its position is a priori unknown, there's no general recipe for solving these problems. You can't just apply an abstract theorem and say, this is all going to be fine. And finally, unlike with the pure Euler equations, where there's a nice change of variables that Gödel used, we aren't aware of any way of forcing this into an autonomous 2x2 system. And so we can't just use a fixed phase portrait analysis to track the trajectories. This is a disadvantage compared to the work for pure Euler, where you can really draw the phase portrait and study it. Here, the phase portrait evolves. There are two explicit solutions for this system, which I'm going to call far-field and Friedmann. The far-field solution, rho little f, omega little f, has the right asymptotics in the far field. The density decays at the right polynomial rate, and the omega converges to the correct value. It is the correct value. However, the density blows up at the origin, and in fact, the value of omega is also not the right value for regularity at the origin. This is tied to the blow up in the density. On the other hand, the Friedmann solution, this has good values at the origin, positive finite density. Omega is exactly the limiting value it should have, but the density doesn't decay in the far field. And so this is non-physical for that reason. Despite this, the presence of these solutions suggests that we can try and use them as barriers or as comparison or reference solutions. And so to fix a little bit of notation, one can check that both of these have a single sonic point at y little f and y capital F respectively. And for all gamma between 1 and 4/3, these are nicely ordered. As I've just said, the far field satisfies the right boundary condition at infinity. And so we're going to try and look for solutions with sonic points between these two values, where we can use the relevant omega functions as barriers and try and trap the solution, the self-similar solution, between these two values. So the proof proceeds in a number of steps. Because solving onto a sonic point is difficult and leads to all sorts of unpleasantness, it's not entirely clear what kind of singularity you should expect a priori. Instead, we try candidate sonic points in the range I just pointed out and get initially a local solution by Taylor expansion. So here, rho j and omega j are functions of y star. So for each y star in the interval, I try and derive a Taylor expansion that gives me a local smooth solution. This is going to be my starting point. To do this, we recall Euler-Poisson in self-similar form. So I've just compressed the notation here so that capital G is exactly the thing telling you whether or not you're subsonic, supersonic, or sonic. And to have a smooth solution through a candidate sonic point y star, well, firstly, capital G needs to vanish at y star. That's what tells me I have a sonic point there. And to have the smooth solution, this h, which is a quadratic, also has to vanish. So solving this relation gives us a smooth one-to-one mapping between values of y star and values of omega naught. There's also a smooth mapping from y star to rho naught, but it's not necessarily injective. But we can use y star and omega naught interchangeably as telling us the location of the sonic point. And so I note here that I'm going between the two reference values, the far field and the Friedman values. Okay, so far so simple. When we get to the first order coefficients, this is where the
one second. Omega 0 is
exactly the value of omega at y star.
Okay.
So it's the zeroth order Taylor coefficient.
And what about rho 0? Rho 0 at y star?
Yeah, so rho 0 is rho of y star.
Here, because you are saying smooth one-to-one mapping between omega 0 and y star. What about the rho 0?
It's smooth from y star to rho 0, but it's not one-to-one.
Okay, so you fix rho 0. So here you fix rho 0, but how are you fixing rho 0?
So it's a smooth function of y star. You can treat rho 0 of y star just as a function. So once I've fixed a y star, that gives me a rho 0.
Okay. Oh, yeah, because here, okay, maybe I'm not understanding very well, because you want h of rho omega to vanish, right?
Yes, yeah.
H of rho omega to vanish. Okay.
So if you think
I see. So you are using, because you have H and G, both are vanishing.
Exactly, I have two constraints.
If you fix omega 0, then you get y star because of the vanishing of G, and then you get to rho 0 because of the vanishing of H.
It's not the intersection of H equals G equals 0. There are the two constraints. So if I fix a y star, that's the easiest way to think about it. That gives me a curve, rho 0, omega 0, that I can sit on. There's only one point on that curve where H also vanishes.
Yeah, okay.
Yeah. When I get to the next order coefficients, the first order ones, this is where the nonlinearity makes itself felt. And so there are two possible curves of solution. So here I should explain what I'm plotting. I've used the fact that there's a one-to-one correspondence between y star and omega 0 to treat omega 0 as the thing that I'm solving in terms of. And then I'm looking for rho 1, effectively, as a function of omega 0, which is equivalent to finding it as a function of y star. There are two possible values that it can take. There's this purple line here, or the red curve, and previously these have been referred to as the Larsson-Penston solution or the Hunter solution. So the original Larsson-Penston solution has its Taylor coefficient on this segment of this curve, this left-hand bit of the purple curve, while all of the Hunter solutions live on the right-hand segment of the red curve. And so this was taken as a distinguishing feature. It's called type A, type B in some of the literature, type 1, type 2 in other parts. As we increase gamma above 1, however, this structure changes. And in fact, there was a hidden degeneracy in the problem. And so what this little GIF is showing is I'm stepping gamma up. So I increase gamma, and I look at what the two possible solution curves are. And they separate as soon as gamma is bigger than 1. In fact, all of the Larsson-Penston and Hunter solutions live on this lower blue curve. So we should think of this as the curve giving all of the known solutions for the isothermal problem. And as gamma tends to 1 from above, the two degenerate. This is really because you're solving quadratics. The quadratic formula has a square root in it. When its argument vanishes, you get this kink. That's what's going on. So this is really a branch selection criterion. It's saying we take the lower branch for rho 1 omega 1. If we do this, we can then construct all of the higher order coefficients just by solving linear systems. In fact, what we find is that rho n omega n can be treated as the solution to a linear problem where the right-hand side is given in terms of all of the lower order coefficients. Via a combinatorial argument, we can construct bounds on all of the coefficients and find that there is a radius of convergence for the power series. This analytic function is then a solution locally on its radius of convergence, which may be small, to the Euler-Poisson equations. So this theorem is just stating this: for any gamma, there is some value of nu, which is the radius of convergence, such that for any y star you give me in the range in which I'm looking for solutions or for sonic points, then I have a local analytic solution on a fixed size neighborhood of y star. This solution has a single sonic point at y star, no other sonic point in this range. Okay, so this is giving me a local solution around a candidate sonic point. And now what I need to know is, can I connect it to the origin smoothly and send it out to infinity with the correct asymptotics? So firstly, going out to infinity, this is the easy direction. In fact, for each of these solutions, which I'm indexing with y star, you can extend them globally to the right out to infinity. They'll always remain supersonic, so no more sonic points form. They'll always satisfy the correct asymptotic boundary conditions. So this is good in one sense, in that you can always have your nice solution, but it gives you no selection criterion for the values of y star. How do we do this? Well, I'm using the nonlinear structures in the equation to find dynamical invariances. I want to show that omega remains trapped between the two reference values. And then using my dynamical invariant regions for various quantities, we show that the flow remains supersonic. And if you've got the global supersonic flow, the asymptotics follow from this structure. So this is a sort of schematic diagram. You pick your y star between y little f and y capital F. To that choice of y star, I've given 3 here, you associate an omega naught. This is the thing that's given to you by solving for the Taylor coefficients. That gives you a local solution around here, and then you shoot it out to the right, and here I've just put infinity at a point. Your value of omega always converges to the correct value. So you can do this for any sonic point in this range. So that's the easy direction. Solving to the left, we want to connect all the way up to the origin. And we want to do it in such a way that omega remains between these two reference values, and it has the correct limit as we approach the origin. It needs to connect smoothly at the origin. So to do this, and I'll show a diagram in a moment, we're going to look for a y star bar that allows this to happen. And we're going to try and find it as an infimum of some set with a nice property. So this is a sort of ad hoc shooting argument. So this capital Y, we're looking at values of y star in the open range, such that the omega touches the critical value before I hit a second sonic point effectively. If I hit a second sonic point, I expect blow up. So this is going to be a connected set. I'm having this property hold for all y star between y star and y capital F. And what I hope is that as I decrease y star, the intersection point with this reference value is going to decrease all the way to 0. Because of the possibility of hitting a second sonic point, we need to worry about uniform controls and uniform continuity properties with respect both to y and to y star. And this is where a lot of the difficulties come from. So schematically, what's going on is I start with a y star that's close to this upper value, and I show that I drop through this reference line. As I decrease y star, the value of omega naught increases, and I hope that the intersection with the reference value decreases all the way down to the origin until I hit a value that connects smoothly. to give me the necessary control over the solutions with as functions of y star, I'm going to try and get monotonicity for both rho and omega. So what I want to know is that as long as I'm in this set capital Y with my little y star, the corresponding omega has to be monotone until it hits this reference value. And this will then give me some kind of uniform control as I tend down to the critical value. Below this value, these lower y stars, what we expect is to hit a turning point where the solution starts increasing again and the monotonicity fails. So the monotonicity is also somehow a distinguishing feature of the correct solution. So I'll try and outline the monotonicity argument. Firstly, just a little bit of notation. Try and find so we call the critical time yc as the first time that my omega touches this reference value, 4 minus 3 gamma over 3. So here I've given, yeah.
Matt, I have a question, like concerning your notation. You are calling it omega of y tilde y star. Maybe if you can go back, maybe even before you introduced. Oh yeah, right. So yeah. So I think when you call your solution, you call it with the second index is the y star, where you put the data, right? The y star is the point.
Exactly.
Okay.
Yeah, that's right. So yeah, so I'm adjusting.
Yeah. Right. So here you want the capital Y is the set where you touch 4 minus 3 gamma over 3. Okay. Yeah. And then you want to prove that the boundary of this set you will touch at 0, right? Or something.
Yeah, okay. That's right. So I define the touching time in the obvious way. So here I've drawn a curve. So I started with some y star tilde, and I've touched at this yc, and it's not clear what the derivative of omega is doing here. But I know that, so this follows from the Taylor expansion, I know I've got local monotonicity around this y star. So I always know that I have a strict sign on the derivative through the sonic point. This just follows from the Taylor coefficients. So what I want to do is to say that I retain monotonicity until I hit this touching time, and that I can do that for all of the solutions that do touch. That's the goal. So that this is an open property follows from some continuity properties of the flow. The tricky direction is to show it's a closed property. And so what I'm going to do is suppose there exists some maximal y star tilde, that's the one I've drawn, such that the derivative of omega hits 0 somewhere. So I lose strict monotonicity somewhere. And as I've drawn it, this is happening at yc. So we now proceed in a number of steps. Firstly, h, this was the numerator in the equations. So I had rho prime equals y h on g, and the omega prime was the linear part minus y omega h on g. So h is giving me monotonicity properties of rho, and it's also controlling possible signs for the derivative of omega in competition with another term. I first show that this has to remain strictly negative on this whole interval. This is a dynamic invariance that comes from the structure of the nonlinearity and the fact that I have a subsonic flow on this region. So what this tells me in particular is that omega prime at the point where it touches the reference value, this is signed strictly. So in particular, the point where the derivative of omega vanishes, so it's omega prime of yc semicolon y star tilde. This is just ruling out the vanishing of the derivative at the end points of this interval. It has to happen in the interior. Next, we show that in fact has a strict sign to the left of the point where it vanishes. So it doesn't just touch zero, flatten off and come down again, as in this picture, but in fact, it truly has to go down, increase, and come back down again. This is delicate as a part of the argument. If we assume that omega double prime is strictly positive, of course, this follows directly. The derivative has to pass through zero. But in fact, to show this property, we have to use the structure of the equations and find a sign on the third derivative of omega at points where the first and second derivatives vanish. And so this is fairly delicate. But what it's saying is that you can't have this basic scenario where you flatten, have an inflection, and come back down again. You pass through zero, so you change direction back. But this is now going to give me my contradiction because I have uniform continuity on this region of omega prime with respect to both y and y star. So I have this because I'm going to be uniformly away from the sonic point. Somehow I'm uniformly away from sonic. And I have various good properties and estimates on the solution on this region. And so in particular, if I take a sequence of y stars that are bigger than y star tilde, and I start decreasing them, the values of omega prime have to converge. But for all of these solutions, by construction, they're all strictly monotone, whereas here the monotonicity breaks strictly. And so there's no possibility for the conversions to hold, hence my contradiction. So this is really using properties at both the sonic point and at the critical touching time. So with this, we're able to propagate the monotonicity of this pseudo-velocity all the way down to the touching time. And this is sufficient to give control over the solutions as we shoot y star. Okay, so this is the one of the key steps in the proof. And if I just return to the definition of capital Y, using the monotonicity, I'm able to show that the y star corresponding to the infimum of capital Y is exactly the function I want. It's strictly monotone all the way down to zero. It hits the critical reference value at the origin. I have nice control over the density, which means I can keep it bounded, and I've constructed a smooth solution. The final step is to show that it's in fact smooth at the origin, not merely C1, say. And this comes, in fact, again, from a Taylor expansion at the origin, which gives me a local smooth solution and a local uniqueness result. But I'm not going to go into that in any detail. So that's the construction and the proof of the main theorem. The future program is, of course, the linear stability of these things. If we work in appropriate self-similar coordinates, we hit a number of difficulties. Firstly, the problem is non-self-adjoint, so in principle, it could have complex eigenvalues. This was one of the things that was an obstacle to the numerical works in the astrophysics literature for a long time. The sonic degeneracy causes issues with type changing and with dissipativity. And here we expect the monotonicity of omega to be helpful. This is connected to various conjectures. And of course, the future directions include the nonlinear stability. And we want to be able to push this into the relativistic direction. So if we couple the Einstein equations to a fluid matter model, then Guo, Hadzik, and Zhang have recently proved that there are, again, self-similar implosion profiles, which are in some sense comparable to these solutions. So the Newtonian problem is interesting in its own right. It gets used in physical modeling, but it also has connections to the relativistic problem. Beyond that, of course, there's the problem of continuing the solutions and the subsequent expansion. And these are all interesting directions. But with that, I will thank you for your attention.
Okay, are there questions? Thank you very much. Are there questions or?
Hi, I have a question actually. So your method provides a solution with just one sonic point.
Yes.
But is it possible to extend the method to include even an odd number of sonic points if it's physically relevant?
So there are solutions that hit a second sonic point.
Yes.
Typically, all of the ones that I'm aware of, they blow up at the second sonic point. So they're not proper solutions to the underlying PDE system because they're not global in Y.
Okay.
So you hit some singularity. This is the case with every second Hunter solution. They pass through one sonic point smoothly, and then they hit a second one eventually, and this leads to blow up rather than to.
So there is no hope neither to extend to a third or a further sonic points. Because of this blow up.
Want to say it's impossible, but if you look at the regularity conditions that you need to pass through the sonic points, you do have various monotonicities that are necessary, and so you would need to show that you could change sign, as you say, to change sign an even number of times to preserve the monotonicities somehow. It's not clear how you would do this.
Okay, and also perhaps it's a remark, the fact that you're using your reference solution, the far field and the Friedman solution to hit the two condition at 0 plus infinity, also tells that there could be no self-similar profiles outside this range of the sonic point. Is it correct?
Not necessarily. The Hunter solutions do have oscillations, which can carry you either side of the reference profiles in principle.
I see.
But you don't hit more sonic points, but you do pass outside and back and try and connect smoothly at the origin.
But it fails the condition at plus infinity in that case, is it?
No, they all satisfy the condition at plus infinity. So this follows, if I go back to the solution to the right, this whole range of candidate points, it includes all the Hunter solutions. They're all fine at infinity. There's no problem there. It's as you come to the left, they could have oscillations.
I see. Okay, yeah. Okay, thank you.
Okay, are there more questions?
So may I have 2 questions, please?
Yeah, please.
Yeah. So first question is that you are proving the existence of a self-similar solution, which is the scaling rate given by the self-similar rate. So do you think that we have a different rate which is faster than the self-similar rate?
You mean looking for type 2 blow-up solutions?
Yeah, that's me, yeah.
It's a very interesting question. I'm not sure is the honest answer. It's possible, but I don't know.
Okay. So my second question is that when you solve in the system ODE, it's really complicated ODE. And then we have the parameters Y star. And I believe that in the numerical simulation computation, it's the value of Y star is very sensitive, even that you perceive it a little bit like epsilon, like 10 to the minus 4, 5. It will change the behavior of the solution. It will change completely the behavior of the solution, and maybe you will hit the blow up in finite interval.
Yes.
So how do you deal with that? Because this Y star is the parameter, you need to choose well the parameter.
So that's why we have this ad hoc shooting method. So, okay, when you're solving to the right, firstly, you don't have this level of sensitivity, it's fine. Yeah. But when you're solving to the left, that's why we really need this delicate shooting argument, because these solutions, once they pass below this reference value, and this will be the case for all of the Y stars bigger than the critical one, we lose control on the behavior. We don't know what's going on. if you pass below there, which we, again, don't want to do, so that's why we shoot from above, they turn at least once, but then in principle, they could have infinitely many oscillations and blow up. We just don't know what happens really, because as you say, it's very sensitive to the value of y star.
Right.
So that's part of the motivation for the construction of the shooting argument in this way, is as long on the interval for which you remain above this value, you have monotonicity. And that gives you the necessary control. So although you don't control the full solution, you control the portion of it that you care about.
Yeah, I see. So it means that theoretically, it's very, that it's very difficult to compute what is precisely the y star, the value of y star. Right?
Yes. Yeah.
But from the numerical simulation, you can predict what the value of y star.
I haven't done it particularly for the polytropic case. I've been doing it for the isothermal case, the gamma equals 1, so the true Larson-Penston solution, and it's something like 2.34101. So you can construct it.
Okay. So it means that when we need to input some related value, like very close to that value to run the...
Yes. Yeah.
That, okay.
And yeah, it has to be very close to that value.
Exactly, yeah.
Yeah.
Okay. Okay, thank you, great.
Okay, are there other questions? So, okay, I have a small question. So if you take this solution that you have, which is, not finite mass, right? So, but then you come and you cut it very far away. You put a cutoff.
Yeah.
What do you expect the evolution to do?
If you cut it very far away, assuming you're cutting it sensibly with physical boundary conditions, we expect that to be completely fine, not to affect the blow-up mechanism.
So it will be exactly the same blow-up mechanism.
Because it's Euler Poisson, the gravitational potential is non-local, right? So it'll have a tiny effect. But if you cut far enough out, the effect should be negligible.
Okay, so this is what you expect. You expect really the blow-up to be stable and okay.
Yeah, absolutely.
So, but do you expect other kind of blow-ups or not? Or you expect this one to be the right one?
So we expect this one to be the right one. There is a self-similarity hypothesis in the astrophysics literature where they say this is the blow-up that they expect.
Okay.
Effectively. In radial symmetry, right? That's
okay, thank you. Are there other questions? No? Okay, thank you very much, Matt.
Thank you.
And then we'll start again in almost like 10 minutes. Okay.